Okay, so now we're going to try to show how to do Lewis structures for the Lewis structure exceptions, and then we'll do them also for ionic compounds and also for resonance. So let's take a look first. How many total electrons do we have to do with your valence electrons? Well, let's see. Beryllium has 2. Chlorine and fluorine are both halogens. They both have 7. So we've got 16 total electrons to deal with. Now remember, beryllium is the first non-hydrogen, goes in the middle. Put the chlorine and fluorine around it. Connect, subtract our 4 that we used. That gives us 12 electrons left. That's 6 pairs. And 1, 2, 3, 4, 5, 6. And this works because beryllium attached to chlorines and fluorines, or just chlorines, is stable with only 2 pairs of electrons around the center atom. Again, it is an exception. Okay, so now let's take a look at the next one. This is PCl4F. In the notes, I gave you PCl5, but it's basically the same thing. Remember, chlorines and fluorines are halogens, so they're in the same groups. Phosphorus has 5 electrons. Each of the halogens has 7, and there's 4 or 5 of them. So 5 times 7 is 35. And we add it up, that gives us 40 electrons. So we put P in the middle, arrange the other ones around it. Okay, connect 1, 2, 3, 4, 5. That's 10. That leaves us with 30 electrons, which is 15 pairs. So let's put them on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now we've used all the electrons. Do you notice that all of the halogens have complete 8 octet electrons? All right. Now this is an exception. Phosphorus and chlorine, and sulfur, as you might see, can have more electrons around the center atom than 8. 2, 4, 6, 8, 10. We've used all 40 electrons. We have none left. And everything fits because we know that phosphorus can have 10. Okay, so let's do the last exception that I wanted to show you. This is sulfur hexafluoride. Again, we're going to count up all of our valence electrons. Sulfur is in the same group as oxygen, it has 6. Fluorine is a halogen. There's 6 of them. Each of them has 7, that's 42. 6 times 7 is 42, so we have a total of 48 electrons. Sulfur goes in the middle. Arrange the fluorines around it. Make that 6, connect them up. Okay, so that takes 2, 4, 6, 8, 10, 12. So knock off 12. That leaves us with 36 electrons. Divide by 2, that's 18 pairs. And sulfur can have more than 8 electrons in valence electrons around it, but the fluorines have to have no more than 8. So we're going to use all of our pairs. There's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, perfect. We've got all 18 pairs used up. We have 0 electrons left. Now, I do want to point out one more thing that's important. When we're talking about exceptions, there are some atoms that will never have an exception. So, nitrogen, carbon, oxygen, and fluorine. These will always have 8 valence electrons. And that's kind of helpful for you to know that. All right? Okay, now we're going to look at how you do Lewis structures for ionic compounds. We still start the same way. We start out by counting valence electrons. We got 1 electron here, we've got 7 electrons there. So total is 8 valence electrons. Now, sodium is a metal, fluorine is a nonmetal. Even if we were to take the time to look at electronegativity differences, we'd see that this is clearly an ionic compound. So what do we do for these? We have to draw them separate from each other. Because they have charges, we put brackets around them. The sodium loses its 1 valence electron and gains a 1 plus charge. The fluorine gains that valence electrons, fills those its last half open p orbital, and gains a 1 minus charge. So that's all you have to do. Ionic compounds are super easy. The nonmetal, you completely fill it. The metal has no valence electrons. It really does. It's got ones from the energy level below the one that was lost. Sodium is in the third energy level, so it loses one, goes down to the second. Okay, now let's take a look at magnesium chloride. Same thing. 2 electrons for magnesium. Each chlorine has 7. That's 14 electrons. 16 electrons total. Again, we're going to have brackets around the ions. Let's see if I can move that down just a little bit. And in this case, we are going to have 3 ions. We have 1 magnesium, which will just be magnesium all by itself because it lost its 2 valence electrons from the third period. Each of the chlorines gains 1 to fill that last hole. So it has a 1 minus charge, and then another chlorine over here with a 1 minus charge. So that's all you got to do for ionic compounds. Now, we're going to move on and look at polyatomic ion, okay? Now, let's take a look at the ammonium ion. Again, we start out the same way as usual, count up all of our valence electrons. However, the plus charge is going to change things a little bit. So nitrogen has 5 electrons. Each hydrogen has 1 electron, and that adds up to 9 electrons. However, with the 1 plus charge, it means we got to subtract 1 electron, 8 electrons. Here is an important hint. You will never, ever have a Lewis structure where you have an odd number of electrons. Are there some that have odd? Yes, but I will never show them to you. They're like exceptions and they're AP level. So we are only going to deal with structures that have even numbers of electrons. Doesn't matter whether it's a polyatomic ion or a covalent compound or an ionic compound. We're only dealing with even numbers. Now, next thing, nitrogen in the middle. Put the hydrogens around it. It's got a charge though. What does that mean? Well, we better put brackets around it and put the charge outside, 1 plus. And then we connect 2, 4, 6, 8. Oh, look, we used them all up. 0 electrons left. That is a good structure. Okay, now we're going to look at a polyatomic ion. Now, polyatomic ions oftentimes have something called resonance, which I'll explain in just a minute. But first, let's do our normal thing. Let's add up the number of valence electrons. Nitrogen has 5. Each oxygen has 6. We got 3 of them. That's 18. That's 23. Hey, that's an odd number, but guess what? There's an extra 1. That's why there's a 1 minus charge. So we've got 24 electrons. Now let's start out by just writing our N and putting 3 O's around it. We know it's an ion, so it's got to have brackets and the charge outside. Now we connect 1, 2, 3. That knocks off 6 electrons, so we've got 18 electrons left. That is 9 pairs. So let's start writing the pairs in. 1, 2, 3, 4, 5, 6, 7, 8, 9. We're done, right? No, we're not. Look at nitrogen. Remember, these 4 elements, nitrogen, carbon, oxygen, fluorine, will never violate the octet rule. So we need to have 8 around the nitrogen in the middle. The only way we can do that is by forming a double bond to one of the oxygens. But the question is, which one? The answer is, it doesn't matter. Because it could be any of them. It all kind of means that all of them are possible. So when we have that, we have something known as resonance. And when we have resonance, we have to draw all possible structures. So we'll put double bond there. Now that's a good structure. But we use little double arrows to indicate that we have other possibilities. We have to draw all the other possibilities. And putting little double arrows between all of them. Let's make it go up this time. And then we have one last possibility over here. So let's see, oxygen, oxygen, oxygen. Let's make the double bond go there, because now we've got all 3. In each of these, they all have a complete octet around every atom, and there's 3 different structures that can do that. Those are called resonance structures, and you have to draw all 3. You can't just draw one. If you count, no matter where you count, they all have got a total number of electrons of 24, each structure that is. And if you look, everybody has 8. 2, 4, 6, 8 around this oxygen, 2, 4, 6, 8 around that oxygen, 2, 4, 6, 8 around the nitrogen, because the bonded ones count for both, 2, 4, 6, and a pair, bonded pair, 8 for that oxygen. So all of those are good examples. All right, let's look at one last example that also has resonance, C6H6. Now, without you knowing this, you wouldn't be able to figure it out. This was actually a complicated problem in chemistry for a long time. But the carbons form a 6-sided ring. Those are our 6 carbons. And there's 1 hydrogen attached to each. Now I'm just going to draw in all the bonds first, and then we're going to count electrons and see where we are. I know I'm doing a little out of order. 6 times 4 is 24 electrons for that carbons, and then 6 for the hydrogens. We've got 30 electrons. How many pairs do we use up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 24. So we have 6 electrons left. Now let's look at all the carbons. There's a problem. Each carbon only has 6 electrons around it. Carbon never violates the octet rule. It needs 8. So there's 2 ways we can do this. One way is like this. But there is a second way. We could have put the double bond here, here, and here to make that add up, by the way. When we use that, that gives us 0 left. So guess what? We now have more resonance structures that are possible. Double arrow. Instead of this one, we're going to do this one. So this stuff is called benzene. These 2 regular structures. You'll actually encounter that more in organic chemistry. But here's one of them. And here's the other one. Those are the 2 resonance structures of benzene.